Assalamu alaikum dear students. Welcome to this lecture. My name is Muhammad Alamgir, your course instructor of physics. This is the topic of today's discussion, that is electric field. In this lecture, we shall discuss field of the forces, electric field due to a small number of point charges, and electric field for a continuous charge distribution in which charges are distributed uniformly and non-uniformly. Then we'll discuss visualization of the electric field and rules for drawing field on two different surfaces, and then how to choose the number of field lines with examples, and finally motion of a charged particle in a uniform electric field. We'll start with the field of the forces. Dear students, as we have studied in previous lecture that Newton's law of gravitation and Coulomb's law enables us to calculate the direction and magnitude of the gravitational and electrical forces. However, there are two questions here. Number one, that what are the origin of the forces? And question number two is how these forces are transmitted from one mass to another mass or from one charge to another charge. Question number one, what are the origin of these forces? The answer of this question is still unknown. Therefore, the existence of such types of the forces are accepted as it is. So, these forces are called basic or fundamental forces of the nature. Now the second question, that how these forces are transmitted from one mass to another mass or from one charge to another charge. Many of the scientists tried to answer it, but only the Michael Faraday was succeeded to find the solution of this question. Michael Faraday has introduced the concept of the electric field to answer this question. Now, according to the theory of the Michael Faraday, that it is intrinsic property of nature that an electric field exists in the space around an electric charge. And this electric field is considered to be a force field that exert a force on the other charges placed in that field. For example, a charge Q produces an electric field in the space surrounding it. And this field exists whether the other charges are present or absent. However, the presence of the field cannot be tested until another charge Q naught is brought into that field. And the field of the charge Q interacts with charge Q naught to produce an electrical force. Now we'll discuss the interaction between charge Q and Q naught. The interaction between charge Q and Q naught proceeds in two ways. Number one, charge Q produces a field around it. And number two, this field interacts with the test positive charge Q naught to produce a force on it. Here a point to be noted, that the test positive charge Q naught has to be very small, that it cannot distort the field which it has to measure. Now we'll discuss the strength of the field. As we can see clearly in this pic, that the density of the dots is proportional to the strength of the field at various points. And we may define the electric field intensity, which is equal to the force exerted on the test positive charge Q naught when it is placed in an electric field, which is shown in this pic. And mathematically, we can write it as E equals to F divided by Q naught. Here F is the force exerted on the test positive charge Q naught. Again, I am going to discuss it,
that the test positive charge Q naught must be very small so that it cannot distort the field. And since the electric field intensity is the force per unit charge, so it is measured in Newton per coulombs in SI units. And we know that it's a vector quantity, so it has same direction as that of the force. Finally, we have to calculate the force on the test positive charge Q naught. That the force experienced by the test positive charge Q naught when placed in the field of the charge Q in a vacuum can be calculated by the Coulomb's law. And we know that here is the medium between both of these charges is a vacuum, and if r is the distance between both of these charges, then we can write it mathematically as F equals to 1 over 4 pi epsilon naught q naught divided by r square, r unit vector. Here r unit vector is directed from the point of the charge q to the test point charge q naught. And by the definition of the electric field intensity, which is equals to the force divided by q naught, by inserting the value of F in equation number 2 from equation number 1, we'll get finally the equation as E equals to 1 over 4 pi epsilon naught q over r square, which is the result of electric field intensity or electric field strength. Now we'll discuss electric field vector at point P due to small number of the point charges. So the electric field vector at point P due to small number of the point charges can be calculated in the following steps. That first we have to calculate electric field vector at point P individually for all of the charges and then add them vectorially. In other words, total electric field vector is equal to the vector sum of all the electric field vectors at point P due to all of the point charges. Then principle of superposition is applied, which follows directly from the vector addition of the electric forces. Therefore, the electric field at point P due to group of source charges can be expressed as a vector sum here in this equation, that E equals to 1 over 4 pi epsilon naught summation I qi over Ri square Ri unit vector. Here Ri is the distance of the ith source of the charge qi to the point P, and Ri is a unit vector directed from qi towards P. Now we'll discuss electric field intensity for a continuous charge distribution. As equation of electric field intensity is useful for calculating the electric field due to small number of the point charges. But in many cases, we have a continuous charge distribution rather than collection of discrete charges. And the charges in this situation can be described as continuous distributed along some line, over some surface, or throughout some volume. Here in this figure, we can see that charges are distributed continuously. Now the question here is, how can we evaluate the electric field by continuous charge distribution? So, to set up a process for evaluating the electric field intensity created by this continuous charge distribution, let's use the following procedure. First, we divide this charge distribution in small elements, each of which contains a small charge del Q. Next, use the equation of electric field intensity to calculate electric field of each element individually at a point P. And then finally, evaluate the total electric field at point P due to charge distribution by adding the contribution of all the charges by using principle of superposition. Consider there is a single charge element. Electric field by the single charge element, let's say del Q, can be calculated as E equals to 1 over 4 pi epsilon naught del Q by R square R unit vector. Here r is the distance between charge element and point P, and the unit vector is directed from the element to the point P. Now the total electric field by all charge distribution at point P is approximately E equals to 1 over 4 pi epsilon naught summation I del Qi over Ri square Ra unit vector. Is used, which refers to the ith element in the distribution. As there are large number of elements and charge distribution is continuous, so total electric field at point P in the limit del Qi approaches to 0 is E equals to 1 over 4 pi epsilon naught limit delta Qi approaches to 0 summation I del Qi over Ri square Ra unit vector, which is equal to integration dq by r square r unit vector. Here the integration is our entire charge distribution. Now we'll discuss about illustration of the charge distribution. To illustrate this type of calculation, our surface are throughout a volume. So when performing such calculations, it is convenient to use concept of charge density along with notations. Now the example number 1. When the charges are distributed uniformly throughout a volume V, then by the definition of volume charge density, it is calculated as rho equals to Q divided by V. And from this formula, we can see that its unit is Coulomb per meter cube. And the other example is when the charges are distributed uniformly over a surface of area A. So by the definition of surface charge density, which is charge per unit area, and mathematically we can write it as sigma equals to Q divided by A. And we know that by the definition, surface charge density has the unit of coulombs per meter square. Here is another example of uniform charge distribution. When the charges are distributed uniformly along a line, then by the definition of the linear charge density, which is charge per unit length, and mathematically we can write it as lambda equals to Q divided by L. And it has unit of coulombs per meter. Now we'll discuss non-uniform distribution of the charges. If the charges are distributed non-uniformly over a volume, surface or line, then the amount of charge dq in a small volume, surface or length element is dq equals to rho dv, dq equals to sigma dA and dq equals to lambda dL. Dear students, now we'll study about visualization of electric field. As we have studied about electric field and its mathematical representation, let's now explore a means of visualizing the electric field in a pictorial representation. And there is a convenient way of visualizing the electric field pattern by drawing the lines called electric field lines, and the idea was first proposed by the Michael Faraday. Now we'll discuss about the electric field lines. As the electric field lines are related to the electric field in a region of space in the following manner. Number 1. The electric field vector is tangent to the electric field line at each point, and the line has a direction indicated by an arrowhead, which is same as that of an electric field vector. And the direction of the line is that of the force experienced by a positive point charge when placed in the field, according to the particle in a field model. And the number of lines per unit area through a surface perpendicular to the lines is proportional to the magnitude of the electric field in that region. Therefore, the field lines are closer together where the electric field is strong, and the field lines are far apart where the electric field is weak.
We'll discuss all of these points in detail in the next slides. Electric field vector is tangent to the electric field line at each point. Here we can see in this figure that there is an electric field line having 2 points, point P and point R. EP is a vector here which is drawn tangent to this electric field line at point P. Also, there is another point R, and we can see here ER is a vector which is drawn tangent to this electric field line at point R, and these both vectors are called electric field vectors. Also, here is another fig. We can see here some electric field lines, and some vectors are drawn tangent to the electric field line. These vectors are called electric field vector, and these are tangent to this electric field line. So the electric field vector is tangent to the electric field line at each point. The line has the direction of the electric field vector, and it is denoted by an arrowhead. Here we can see in this fig that the lines have the direction of the electric field vector and are indicated by an arrowhead. Also, the direction of the line is that of the force experienced by the positive charge when it is placed in the field of another charge according to the particle in a field model is shown here in these figs. That when a test positive charge is placed in the field of a positive charge, then it will experience a force of repulsion. So the electric field line has the direction of the force which is radially outward. Also, when a test positive charge is placed in the field of a negative charge, then it will experience a force of attraction. So the electric field line has the direction of the force which is radially inward. The number of lines per unit area through a surface perpendicular to the lines is proportional to the magnitude of the electric field in that region. Here we can see in this fig. Therefore, the number of lines per unit area through a surface perpendicular to the lines, if increases, then the magnitude of the electric field also increases in that regions. And if the number of lines per unit area through a surface perpendicular to these lines decreases, then the magnitude of the electric field also decreases in these regions. The strength of the electric field can also be represented with the electric field lines. That if the field lines are closer together, then electric field is strong. And if the field lines are far apart, then electric field is weak. As we can see here in this fig, that there are three different quantities A, B and C. Here the density of the electric field lines around these three objects, which reveals that the quantity of charge on C is greater than that on B, which is greater than that on A. Or we can see it as the quantity of charge on A is smaller than that on B, which is smaller than that on C. Now we'll see the magnitude of the electric field on two different surfaces. As here we can see in this fig, there are two surfaces, surface A and surface B. Here the density of the field line through the surface A is greater than that of surface B. So the magnitude of the electric field is larger on surface A as compared to the surface B. Furthermore, the field is non-uniform here because the lines at different locations points in different directions. Here is a question that is this relationship between the strength of the electric field and the density of the field lines consistent with equation E equals to 1 over 4 pi epsilon naught del Q by R square R unit vector. So the expression we obtained for E using Coulomb's law. So to answer this question, we have to consider an imaginary spherical surface of radius R, which is concentric with a point charge. And from symmetry, we know that the magnitude of the electric field is same everywhere on the surface of this sphere. And the number of lines n that emerge from the charge is equal to the number that penetrate the surface. And hence,
The number of lines per unit area on the sphere is n divided by 4 pi r square. And here 4 pi r square is the surface area of the sphere. And because E is proportional to the number of lines per unit area, so we see that E varies as 1 over r square. And this finding is consistent with equation E equals to 1 over 4 pi epsilon naught del q by r square, r unit vector. Now we'll discuss about the electric field lines due to a single positive point charge. Here we can see in this fig the electric field lines due to single positive point charge. At the field lines lies in the plane due to positive point charge, as we can see here in this fig. Here these lines are directed radially outward in all the directions, because here the positive charge experiences a force of repulsion. Similarly, the electric field lines due to a single negative point charge is shown here in this fig. As the electric field lines representing the field due to a single negative point charge are directed toward the charge. And in either of the case, the lines are along the radial direction and extend all the way to infinity. Also notice that the lines become closer together as they approach the charge, indicating that the strength of the field increases as we move toward the source charge. Now we'll discuss the rules for drawing the electric field lines. And the rules for drawing the electric field lines are as follows. Electric field lines must begin on a positive charge and terminate on a negative charge, which points in direction that if a positive charge would accelerate if placed upon the line. Here we can see in this fig. There are two parallel plates. One plate has positive charges and the other plate has negative charges. Here the electric field lines are directed from positive to negative charges. Also, we have two charges. One is positive and the other is negative. Also, we can observe here the electric field lines indicated by an arrowhead are directed from the positive toward negative charge. And there is another case. When there is an excess of one type of the charge, then some of the lines will begin or end infinitely far away. As we can see here in this fig, when two positive charges are placed together, here the electric field lines are shown and the direction of the electric field lines are indicated by an arrowhead. These lines will begin on a positive charge and will end infinitely far away. Also, we can see here two negative charges are placed together and the electric field lines are shown here and the direction of the electric field lines are indicated by the arrowhead. These lines will begin infinitely far away and will end on these negative charges. And one of the rules is the number of the lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. That means if the magnitude of the charge increases, then the number of lines drawn also increases. And if the magnitude of the charge decreases, then the number of lines drawn also decreases, as we can see here in this fig. That the density of the electric field lines around these three objects reveals that the quantity of charge on C is greater than that on B, which is greater than that on A. Also, we can read it as the quantity of charge on A is smaller than that on B, which is smaller than that on C. Now the last one rule is no two field lines can cross each other. As we can see here in this fig, electric lines of force never intersect each other because at the point of intersection, two tangents can be drawn to the two lines of force. This means two direction of electric field at the point of intersection, which is not possible and is physically incorrect. Now I am going to recall
all of the rules for drawing the electric field lines. The rules for drawing the electric field lines are: the lines must begin on a positive charge and terminate on a negative charge. And in case of any excess number of one type of the charge, some of the lines will begin or end infinitely far away. And the number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. Also, two field lines can never cross each other. Now we'll discuss how to choose the number of field lines. As we choose the number of field lines starting from any object with a positive charge q plus to be cq plus, and the number of lines ending on any negative charge q negative to be cq negative. Here I am using C. C is an arbitrary proportionality constant, and C is chosen such that the number of lines is fixed. For example, in a two charge system, if the object 1 has charge q1 and the object 2 has charge q2, the ratio of the number of lines in contact with the charges n2 over n1 equals to magnitude of q2 over q1. Discuss about the electric field lines of two equal and opposite charges. As the electric field lines for two equal and opposite charges is shown here in this fig. As we can see, the electric field lines are directed from positive to negative charge, indicated by an arrowhead. Here the charges are equal in magnitude, that begins at positive charge must equal in number that terminate at the negative charge. So the points near the charges, here the lines are nearly radial as for a single isolated charge. And the high density of the lines between the charges indicate a region of strong electric field. Now we shall describe about the electric field lines of two same positive point charges, as we can see here in this fig. Again, the lines are nearly radial at points close to either charge, and the same number of lines emerges from each charge because the charges are equal in magnitude. And because there are no negative charges available, so the electric field lines end infinitely far away. And at great distances from the charges, the field is approximately equal to that of a single point charge of magnitude 2q. Finally, we'll discuss the electric field line between charge plus 2q and a negative charge q. The sketch of the electric field lines between charge plus 2q and a negative charge q is shown in this fig. Here the number of the electric field lines that begin on charge plus 2q is double in number that ends on charge negative q. And only half of the electric field lines of plus 2q reach at negative q. And we assume that half of the lines which terminate negative q are to be at infinity. So the electric field lines are equivalent to those of charge plus q at distances much greater than the charge separation. I would like to share this point that electric field lines are not the paths of the particles. The electric field lines represent the field at various locations, and except in a very special cases, they do not represent the path of a charged particle moving in an electric field. Also, I would like to make you know that electric field lines are not real, and these are not material objects, and these are only used for pictorial representation to provide a qualitative description of the electric field, and is only a finite number of lines from each charge can be drawn, which makes it appear as if the field were quantized and exists only in certain parts of the space. Also, the field in fact is continuous and existing at every point, and avoid obtaining the wrong impression from a two-dimensional drawing of the electric field lines used to describe a three-dimensional situation. Now we'll discuss about the motion of a charged particle in uniform electric field. For this, consider a charged particle
of mass m and charge q is placed in an electric field, then it will experience a force which is equal to QE vector. And if it is only the force on the charged particle, then it causes the particle to accelerate according to a particle under a net force model. Therefore, F vector is equal to QE vector, which is equal to MA vector, and A vector equals to QE vector divided by M. Now we'll discuss the case. If the electric field is constant and the particle is free to move, then the electric force on the particle is constant. And if the electric force on the particle is constant, then we can apply the particle under constant acceleration model to the motion of the particle. And the particle in this situation is described by the three analysis model. Number one, particle in a field, particle under a net force, and number three is particle under constant. Now we'll discuss about direction of the acceleration. Direction of the acceleration depends on the charge. If the particle has a positive charge, then its acceleration is in the direction of the electric field. And if the particle has a negative charge, then its acceleration is in the direction opposite to the electric field. Dear students, if you have any question or any concern regarding this lecture, you may directly contact to my WhatsApp number or you may comment on this YouTube video. Stay safe, stay blessed, have a great day. Allah Hafiz.